Why does a ball eventually stop rolling? How does a rocket even get off the ground? The answers might seem super obvious, but today we're going to break it all down and build our understanding of motion from scratch. We're going to dive into the architecture of force, that invisible blueprint that actually explains every single change in motion in the entire universe. So let's start with the most basic question of all. What is it that even needs an explanation?
So, first things first, what are we even trying to figure out here? See, in physics, the goal isn't to explain why things stay the same. The real puzzle, the thing that actually requires a cause, is change. Think about it like this. A book just sitting on a table, that's its natural state. It's stable. We don't really need a special reason for why it's just staying put. But a tennis ball getting slammed by a racket? Whoa. Now that is a moment of serious, dramatic change. Its speed, its direction, it all gets altered in an instant. That is what we need to explain. That's the whole game in physics.
And that brings us right to the heart of it all. This is the central question for this entire explainer. If starting, stopping, speeding up, slowing down, or making a turn are the things that need a cause, then what exactly is that cause?
Well, the answer is one simple, powerful word: force. But force is so much more than just a push or a pull. It's a really deep concept, and to actually get it, we need to peel back the layers.
Okay, so to really understand force, the first thing we've got to do is bust a common myth. This idea that an object has force. It just doesn't. Force isn't a property like an object's color or its weight. It's an event. It's an interaction that happens between two different objects. For instance, when you push on a wall with your hand, that's the action. But at that exact same moment, you can literally feel the wall pushing back on your hand, and that's the reaction. You can't have one without the other. Every single force in the universe is part of a pair like this. It's always a two-way street, no exceptions.
But hang on a second. If forces always come in these neat little pairs, why doesn't everything just cancel out all the time? Well, this leads us to the really crucial difference between balanced and unbalanced forces. This is the real secret to understanding why things move, or why they stay put.
Check out this apple, just sitting on a table. Are any forces acting on it? Oh, absolutely. Gravity is pulling it down, constantly. So why isn't it falling through the table? Because the table is pushing back up with an equal and opposite force. Physicists call it the normal force. These two forces are perfectly balanced. They cancel each other out completely, which gives us a net force of zero. And a zero net force means, you guessed it, zero change in motion. And this idea of net force, it's the whole key. It's the grand total, the overall sum of all the forces acting on something. When that total adds up to zero, an object's motion doesn't change. But when the forces are unbalanced and you've got some net force left over, well, that's when the magic happens. That's when things start to move. This tug of war is the perfect example. It's so clear. If the team on the right is pulling with more force than the team on the left, the forces are now unbalanced. There's a net force pointing to the right, and what happens? The crate accelerates in that direction. It's always the unbalanced, leftover force that causes a change.
Okay, now we've arrived at what might be the most profound and honestly the most counterintuitive idea in this whole explainer. It's a concept that completely changed how we see the universe, and it's called inertia.
And here it is. This is the big one. Our intuition, our gut feeling tells us that you need to keep pushing something to keep it moving. But that's just wrong. If you could slide a hockey puck on a perfectly frictionless surface, it would just keep on sliding, forever, at a constant speed, in a perfectly straight line. Motion itself doesn't need a force, only a change in motion does.
And that natural tendency for an object to just keep on doing whatever it's already doing, whether that's sitting still or moving at a constant speed, that has a name. We call it inertia. You can think of it as the universe's built-in resistance to change. So how do we measure this resistance, this inertia? Simple. We use mass. It's really easy to change the motion of a little toy car with low mass. But try doing that to a heavy cabinet with high mass. It's incredibly difficult. More mass simply means more inertia, which means it puts up a bigger fight against any force trying to accelerate it. Okay, so we have all the pieces of the puzzle on the table now. Force is an interaction. Only the net force is what matters, and inertia is what resists any change. Now, let's put them all together and see how this amazing architecture explains motion out in the real world.
Let's circle back to our very first question. Why does a sliding book stop? Well, let's look at the forces. Vertically, gravity pulling down and the table pushing up are balanced, so nothing happens there. But horizontally, there's an unbalanced force, friction, and it's acting in the exact opposite direction of the book's motion. This net force is what causes the book to slow down or decelerate. Mystery solved.
What about a race car? It might be cruising along at a constant speed, but look, it's constantly changing direction as it goes around the track. And you have to remember, a change in direction is a form of acceleration. The car's inertia wants it to fly off in a straight line, but there's a force from the tires on the road that's always pulling it toward the center of the turn. That net force is what makes turning even possible.
And how about a rocket launch? The upward force of thrust coming from its engines has to be way greater than the downward pull of gravity, which we also call its weight. This creates a massive, unbalanced net force pointing up, and that's what shoves the rocket skyward and accelerates it into space.
So, the whole architecture is complete. We've seen that force is an interaction between objects, but it's the unbalanced net force that actually changes an object's motion. And that change is always being resisted by the object's own inertia, which we measure as mass. This whole dynamic, this cosmic tug-of-war between net force and inertia, is what governs all motion in the universe.
And when we step back and look at the big picture, we can see that force is kind of like the central gear in the whole machine of physics. It's the why that connects motion, which is the study of how things move, with energy, which is basically the ability to cause change in the first place. Force is the mechanism that makes it all tick.
And all of this leaves us with one final, much deeper question. We figured out that force explains the change in motion. But what explains force itself? Why does gravity even exist? Why do magnets pull on each other? To answer that, you have to go even deeper, into the bizarre world of fields and space-time and the fundamental interactions of the universe. Force, as it turns out, is really just the beginning of the story.